Swayam Prabha. Digital India. Educated India.
Welcome to this lecture 26, in which we will continue with the previous lecture's unfinished portion, that is graphical representation of groundwater quality. Continued, and after this we will move on to a new chapter, that is on surface and subsurface explorations of groundwater. So here we have already discussed, that is in the previous lecture, the graphical representations are of the type vertical bar graphs, followed by trilinear diagrams, followed by radiating vector diagrams, followed by circular diagrams, followed by semi-logarithmic diagrams, and there is one last there is another method of graphical representation, that is known as the pattern diagrams. So in this, the first two methods we have already discussed in the previous lecture. So we will move on to the third method, that is the radiating vector diagram. In this radiating vector diagram, so the concentration, the sample identification number is written, and in this, each of the, so there are 6 lines which are at 60-degree orientation, and the length of each line, and of course the order is maintained same. So here always the vertical line represents the sodium plus potassium concentration, the length, and of course the length of each of these lines represent is proportional to the concentration. The next, the 60-degree line represents the magnesium concentration, the length of the 60-degree line, and from the vertical. Similarly, the length of the 120-degree from the clockwise from the vertical represents the bicarbonate concentration. The length of the 180-degree or vertically downward line represents the chloride concentration, and the length of the 240-degree line clockwise from the vertically upward line represents the sulfate concentration, and then lastly the length of the 360 line clockwise from the vertically upward line, or 60-degree from the vertically anti-clockwise from the vertically upward line represents the calcium concentration. So here, say this is the, so in this the sample identification number and then if there is another sample, so this is 1, and then say this is so this is sample 2. So in this case, so again the same thing, so this could be the same pattern is maintained, and at 120 degree it is HCO3, and so here, so it could be the chloride concentration, and it could be, so this next line is the sulphate concentration, and then followed by, so this is the calcium concentration. This is for sample 2. So these are the radial vector diagrams. So basically, and each at the length of this one, there is the lengths represent the concentration in milli equivalent per liter. So this is the radiating vector diagram. So now we will go to the next graphic representation, that is the circular diagram. So in this, basically, so these are the pie charts, and so the area of the circle represents the total the area of the circle represents the total ionic concentration, and in this case, say this could be Na sodium plus potassium, and this could be chloride, so this could be sulphate, so this could be bicarbonate, then this could be calcium, this could be magnesium. So the circle's area is proportional to total ionic concentrations, and the sector in each of the circle represents a fraction of this total ionic concentration occupied by respective ion, whether it's a positive ion or a negative ion. So this is sample 1, and then similarly for sample 2. So if the concentration is less, so it is represented by a smaller circle, and within this, so this could be Na plus K, and this could be chlorine, so this could be sulphate, so this could be bicarbonate, and this could be calcium, and then this could be magnesium. So this is sample 2. So like this, using these circular diagrams, which are essentially pie charts, and so here of course there is a scale for radius, because the area of the circle varies as the radius. So therefore here there is a scale, and then so in milli equivalent per liter. So this is a circular diagram. Next we will go to and of course, so this is also the circular diagram. So here also, so this is also taken from the source, that is Hem in 1970. Next we will go to the other graphic representation, which is the semi-logarithmic diagrams. So in this, so this is taken from the source, that is Scholar, (1962), and here so essentially, so there are lines corresponding to each of the ion, like calcium, magnesium, then sodium, then bicarbonate, sulfate, and then chloride. And here, so this line, the vertical line, represents the concentration in logarithmic axis. So this is 0.1, so this is 1, and then this is 10, and maybe here, so this is 100, and then this, so it could be, say, for one sample. So if this is the constant, this ordinate indicates the calcium ion concentration, then this ordinate indicates a magnesium ion concentration, this ordinate indicates a sodium ion concentration, and then this ordinate indicates the HCO3 ion concentration, and this point indicates the sulfate ion concentration, and then this point indicates the chloride ion concentration, and all these are joined. So this could be sample 1, and similarly for, say, another sample, so the calcium ion concentration could be this much as indicated in this scale, and again, so the magnesium ion concentration could be this much, the sodium ion concentration could be this much, then the bicarbonate ion concentration could be this much, sulfate ion concentration could be this much, and the chloride ion concentration could be this much. So therefore, join each of them by straight line. So this represents sample 2. And here, so these concentrations, so these are in milli equivalent per liter. So this is the another method of graphical representation of groundwater quality, and then lastly we will discuss the pattern diagram. So that is the And this pattern diagrams, again this is taken from the same source, that is Hem from 1970, and here, so from a vertical line the cations are represented to the left. So this is cations in milli equivalent per meter per liter, cations concentration, and then similarly the anion concentration. So that is in milli equivalent per liter, and here for each of the sample, like so in this, so along the top one represents Na plus K on the cation side or the left side, and the along the same line, along the right side it represents the chloride concentration. Similarly, the second line represents the calcium concentration, and along the same line it represents the bicarbonate concentration, and then along the third line it represents the magnesium concentration, and along the right side line it represents the sulfate concentration is represented, and then the bottommost line, so it represents the iron concentration, and here it could be the carbonate concentration. So basically in this case, so there are 4 cations and then 4 anions. So in this case, say for example a particular sample doesn't have iron or as well as carbonate. So in that case both this will be 0. So then if it has a certain magnesium concentration, certain sulfate concentration, then certain calcium concentration, and certain bicarbonate concentration, and then lastly it has certain sodium plus potassium concentration, and then certain chloride concentration. So in this case, so this represents, so this is sample 1. So basically, and in this, and then similarly suppose there is another sample which has say this much of sodium and potassium concentration, and this much of chloride concentration, and this much of calcium concentration, and this much of bicarbonate ion concentration, and say this much of magnesium concentration, and this much of sulfate concentration, and maybe this much of iron concentration, and then this much of carbonate concentration. So in that case simply join each of them. So this represents sample 2, and so on. So like this, the graphical representation, so basically they indicate through this the lengths, we indicate the maybe 10, 20 and so on. So this is so these are the 6 different types of graphic representations of groundwater quality, and now we will move on to the new module So, that is on surface and subsurface explorations of groundwater, and explorations or investigations of groundwater. So, in this lecture we will discuss the geological methods, followed by geophysical methods. So, in the geological methods, let us discuss the remote sensing, and in the geophysical method, let us discuss this electrical analogy. Electrical resistivity, I am sorry. So, this firstly this surf, and of course, all this they belong to the surface investigations of groundwater. And after completing the surface investigations of groundwater, so we will move on to the subsurface investigations of groundwater. And here one thing we should realize, the surface investigations of groundwater, so they are simple and less expensive. Therefore, the amount of information obtained after analyzing the surface investigation data is incomplete. So, this needs to be supplemented by appropriate subsurface investigations. So, now let us move over to the geological methods. methods of surface investigation of groundwater. And here, so basically, so it involves collection, that is data collection, analysis, and hydrogeological interpretation of maps, aerial photographs, geologic maps, geological maps or logs, other records. And here, so this must be supplemented by, it needs to be supplemented by field surveys or reconnaissances or reconnaissance, stream flow, and springs data, well yields, groundwater recharge or discharge, or levels. So only when it is supplemented, so it will give some so here the knowledge of deposition, erosional events, may indicate the extent and regularity of aquifers or water bearing formations. Also, the type of rocks rock formations, indicates so here this is not only rock, it is soil or rock formations, indicates the magnitude of water yield this stratigraphy and geological history may reveal or say provide aquifer details. The natural thickness of overlying layers and dip of water bearing layers may indicate the estimates of drilling depths. Likewise, confined aquifers may provide information about flowing or artificial wells, etc. Landforms may indicate about unconsolidated formations, acting as aquifers, sand dunes, glacier outwashes, etc. So, basically in this geological methods, so we will try to get the as much data from the aerial photographs as well as from the ground details. And now let us go to this remote sensing. So, this remote sensing photographs, which is generally abbreviated as RS. So, RS photographs at various electromagnetic wavelengths provide vital groundwater information. So this RS has developed very fast in the recent years. Recent developments in RS, in remote sensing, has resulted in lot of water resources related applications. And here so the observation patterns, colors, relief, can enable us to distinguish the different the differences in geology, soil moisture, vegetation and land use. So this photogeology can help in differentiating rock or soil types, permeability, aerial distribution, areas of groundwater recharge or discharge. Maps can classify areas into maps which can classify areas into say good, fair or say poor groundwater yield can be prepared. Now let us list the tabular, so the surface features. So this is the table of surface features identified on aerial photographs. Which assist in groundwater condition evaluation. And this is taken from source is Heath and Trainer 1968 and Mollard 1968. So here firstly there will be details of topography, and there will be details of phreatophytes. Basically they are the plants at the surface of ground, that is on the ground surface or say even water surface, and aquatic plants. So this is the second data, and thirdly there is geologic landforms, expected to contain relatively permeable strata then it is followed by, we can also identify these lakes and streams. So lakes means they could be natural or they could be reservoirs constructed out of dams, or so there could be moist depressions and seepages there could be springs, and lastly there could be artificial water features like wells, developed springs, reservoirs, canals, etc. So all this can be identified in this table of surface features, and say for example, if there is an aerial photograph which shows say dense vegetation like this, so then it is an indication of the availability of so this aerial photograph showing dense vegetation of surface plants, so indicating shallow groundwater availability. and here, so this could be the scale, and say maybe kilometers, and this could be the north direction. So by identifying this this dense vegetation of surface plants or phreatophytes, so we can conclude that there is shallow groundwater availability in that area. So next we will go to the geophysical exploration. So in the geophysical exploration, so this scientific measurements are carried out to obtain hydrogeological properties regarding the mineral deposits as well as geological structure. And so with the discovery of oil in say 1926, so this geophysical explorations have become more common. In recent times, so geophysical explorations are being widely used for groundwater investigations. So these geophysical explorations they detect anomalies or differences in physical properties within Earth's crust. So here, so some of the properties like density, magnetism, elasticity, electric resistivity, can be easily measured in geophysical explorations. And so this electrical resistivity method is a very important geophysical method under the for groundwater exploration. So, this electrical resistivity, which is abbreviated as ER. So, this ER is the resistance in ohms between opposite faces of a unit cube of material. So, this ER, the electrical resistivity, which is also denoted as rho. So, this is equal to R into A divided by L, where this R is the resistance So, this is in ohms, and A is the sectional area in meter square, and L is the distance between opposite faces. So, that is in meters. So, this electrical resistivity, so it will be in terms of ohm meters. It has units of ohm meters, and this one, the electrical resistivity. So, we will discuss about the electrical resistivity in the next lecture. Thank you.